Up until yesterday, we unequivocally accepted that light or electromagnetic radiation is a wave. But yesterday we learned something else. Not that light isn't a wave, but rather that light is a wave and a particle. It has both a particle nature along with the wave nature. We call it a wave-particle duality. So prior to 1887, the decision is made. Just about everybody agrees, light's a wave, right? We've got electromagnetic radiation, the whole theory put forth by Maxwell. We've got Hertz's verification of Maxwell's theory of EMR. We've got those 4 properties of waves that are exhibited by electromagnetic radiation: refraction, diffraction, interference, polarization. Okay, light's a wave. But then in 1887, Heinrich Hertz, same guy that performed that spark gap apparatus, performs an experiment called the photoelectric effect. And he discovers that sometimes light striking a piece of metal will cause an electron to be ejected. Fine. But then he tries to explain that. He tries to explain the observations that were made using the wave theory of light, and it just doesn't work. The wave theory doesn't explain all of these observations that were made. Fast forward 18 years, 1905, Einstein. For the first time, we're talking about Albert Einstein. He put forth a theory called photon theory. He said that just like a rock being thrown out of your hand, or a dodgeball being thrown out of your hand, is a particle characterized by a certain energy, he said that light is a particle characterized by a certain energy as well. Light is a photon, a quantum of energy, or a little bundle of energy. Well, it seems kind of ridiculous. Light's a wave, but it's also a little particle of energy. That doesn't make any sense. It can be both. But Einstein's theory, this photon theory that light is a quantum of energy, explains the photoelectric effect perfectly. All the observations that were made, and we'll talk about those observations in a little while after we check over our homework, all those observations were explained perfectly by Einstein's photon theory. So we now, post-1905, accept the wave-particle duality of light. Yes, it still has its wave nature, but now it's also got a particle nature. We'll talk a little bit later on, not today, but later on in the year, about the wave nature, the wave and particle nature of light. We'll talk about the wave and particle nature of things like electrons and baseballs. If light can have a particle nature, then why can't a baseball have a wave nature? We'll talk more about that, as I say, in the upcoming days here. So light is a particle, a quantum of energy. Okay, it's characterized by a certain amount of energy, just like that rock being thrown through the air is. But it's not kinetic energy like the rock has. Rather, it's photon energy. E is equal to h times f, or we could say E is equal to hc over lambda. E stands for energy. It can be measured in joules or electron volts. F stands for the frequency of the EMR. Lambda stands for the wavelength of the EMR. C stands for the speed of light. H, this is kind of the odd one. H is a constant. We call it Planck's constant, named after a guy named Max Planck, who kind of laid the foundations for quantum theory. The value of Planck's constant, well, the values of Planck's constant, 6.63 times 10 to the minus 34 joule seconds, and 4.14 times 10 to the negative 15 electron volt seconds. We talked yesterday about why we can have 2 separate values for Planck's constant. We really don't. It's really the same thing. It's like saying the speed limit, okay, is 100 kilometers per hour, or the speed limit is 62 miles per hour. It's the same thing. It's just 2 different numbers that illustrate exactly the same thing. Same deal here. All right, 3 bits of homework last night. The first set that you had was on page 706. Any issues with any of those 3 questions on 706, please? All 3 of those are good? You guys can convert from electron volts to joules? All right. How about the practice problems on page 707? Number 1. Okay, 1 and 3, yeah. Number 1 says, what's the frequency of a 10 nanometer photon? I'm probably going to circle that because I don't want to be in nanometers. I want to be in meters. What's the frequency of that photon? Now, the temptation when we're doing a question like this is to go straight to the equation that I just showed you. E is equal to hf or E is equal to hc over lambda. That can actually work, but it's not the easiest way to do this. The easiest way to do this question is to go back to physics 20, actually. V is equal to F times lambda. Rearrange it. F is equal to V over lambda. V is the speed of light. So we're just going to call it C, actually. 3 times 10 to the 8 meters per second divided by the wavelength, which, be careful here, it's not 1 times 10 to the minus 9. It's 10 times 10 to the minus 9. It's a nanometer. It's not a nanometer. It's 10 nanometers. So it's 10 times 10 to the minus 9. Do the math there, and we should end up getting 3.0 times 10 to the 16. Is that right? Yeah. Okay. What kind of EMR would that be, by the way? Visible light was 4 to 7.5 times 10 to the 14. X-rays were 10 to the 17 to 10 to the 20. What's this? What's in between visible light and X-rays? Yeah, that would be ultraviolet. Okay, in between visible light and X-rays. Okay, number 3. How many photons of green light with this wavelength are required to deliver 10 joules of energy? Whenever we're looking for a number, then the amount of something, the number of something, it doesn't matter whether it's photons or electrons or oranges in a bag. Whenever we're looking for the number of something, we're going to take the total amount and divide it by the amount for 1. Okay, if I was finding the number of electrons like I did in Unit 2, I would say the total charge divided by the charge for 1 electron. Okay, you guys did that a bunch of times in Unit 2. If I was trying to find the number of oranges in a bag, I would take the total mass of the bag and divide it by the mass of 1 orange. If I'm trying to find the number of photons, then I'm going to take the total energy and divide it by the energy of 1 photon. Now, the total energy here is 10 joules. The energy for 1 photon is, we don't know, but we can find it, hc over lambda. Now, you're solving for energy here. We got 2 values of Planck's constant. Which value do you think you want to use here to find the energy of 1 single photon? Technically, you could use either one, right? But Dustin, which one makes the most sense to use here? Why? Why 6.63 joules seconds? Good. Gives us an answer in joules, which is exactly what we want because we have the total energy in joules. If you use 4.14, you could do that, but you'd get an answer in electron volts, and then you'd have to convert this to electron volts, get the same answer, but it would be kind of a roundabout way to do it, right? So get this number, plug it in right there, and then solve for the number of photons, and I assume it works out to be 2.8 times 10 to the 19. Who asked for number 3? Who was that? Is it good? Good? Okay. All right, the last bit of homework we had was on page 708. Let's take a look at these questions, please. Any issues with these 2? Number 2? Anybody for number 2? Okay. Let's do number 2 here. I think if you can get number 2, you're probably going to be okay with number 1. So let's look at that. If you're still struggling with number 1 after that, then let me know and I'll give you a hand with that one as well. Number 2 says how many? All right, how many? It's a number, right? It's a number. Whenever we're looking for a number of anything, it's total something divided by the something for 1. In this case, it's going to be the total energy divided by the energy for 1. Now, what's the total energy here? What's the total energy? Well, power, this is power, right? 10 watts. But a watt is a joule per second. So 10 watts is the same as 10 joules per second. Now, we're looking for the number of photons in 1 second. So if the power is 10 joules of energy per second, and we only have 1 second, then the energy in this case would be 10 joules, right? If power is equal to energy over time, and power is 10, and time is 1, then energy is equal to 10 joules. Only because we're dealing with 1 second here. That's my total energy. What's my energy for one photon? Let's do exactly the same thing as we just did. E is equal to hc over lambda. Solve for energy in joules using the 6.63 value, and then plug it back into there, do the math, and it should work out to be 2.0 times 10 to the 19. So what's the difference between this question and the last question we just did? This. They make it seem more complicated because they give me a power. But power is joules per second. And we're looking for the number of photons per second. So basically, they give me the energy, just like they did in the last question. They just don't make it, they disguise it. They trick me into thinking that I'm not giving the energy there. Right? Good there? The demonstration that we just did shows us the photoelectric effect, what happens, the observations that are made with the photoelectric effect. It also shows us why the wave theory of light doesn't explain it properly and why the particle theory of light does explain it properly. What is the photoelectric effect? Well, we've briefly touched on this. It is a phenomenon discovered in 1887 by Heinrich Hertz, explained by Einstein in 1905, a phenomenon in which light strikes a piece of metal or some other material, but usually metal, which sometimes causes electron or electrons to be ejected. Sometimes, not always, but sometimes. Prior to 1905, when the explanation, the good, correct explanation came through from Albert Einstein, prior to that, it was very well established what would happen in all of the circumstances that we just showed in the demonstration. We knew that a little bit of light maybe wouldn't cause an electron to be ejected. A lot of light wouldn't cause the electron to be ejected. A little bit of light did cause an electron to be ejected. A lot of light would cause a lot of the electrons to be ejected. Everybody saw that, but nobody could explain that using the wave theory of light until 1905, when we had the particle theory of light or the photon theory of light. Einstein said that since light's a particle whose energy is related to the frequency, in other words, since we've got a little quantum of energy, a little photon, whose energy is related to the frequency, we didn't need more light, more flashlights to cause an electron to be ejected. That does nothing. More light does nothing. It's brighter light. You can see better. That's about it. But it's not going to cause the electrons to be ejected if a single photon didn't cause the electrons to be ejected. What we need is more energy by changing the frequency, by increasing the frequency from ultraviolet to X-rays, or from infrared to visible light. More frequency, more energy. If you're going to cause an electron to be ejected, that's how you do it. You get more energy to the electron. The higher the frequency of EMR you have, the higher the energy. And the higher the energy you have, the more likely you are to eject that electron. We're going to define two terms here. One is called the threshold frequency. And the symbol for the threshold frequency is F0. That's a term that you see more in actually the UK. I don't know if you've ever seen, Fraser, if you've ever seen that subscript 0 before, something like, not necessarily in this context, but sometimes it would be called F naught. You ever heard that? Okay, so F0 would be F naught. Okay, again, it's more of a UK term. Okay, F0 or F naught. Okay, the threshold value. It is the minimum frequency of the EMR, or the minimum frequency of the photon, necessary to eject an electron. A photon below that frequency won't cause it. That was the piece of paper in our demonstration, right? A photon above that frequency will cause the electron to be ejected. That was the calculator or the hole puncher in our demonstration, in our analogy. So it's the minimum frequency of a photon necessary to eject an electron. The work function closely related to the threshold frequency, given by the symbol capital W, just like the symbol for work was in physics 20. The work function is the minimum energy necessary to eject an electron. Now, I'm going to put in brackets another definition for this that kind of goes along with it. It's the minimum energy of the photon necessary to eject the electron. It also corresponds to the energy that gets used up in the process. As you eject an electron, some of the energy gets used up. You got to burn some of that energy to eject the electron. That energy that you burn, that you use up, corresponds to the minimum energy of the photon necessary to eject the electron. In other words, you have to exceed the amount of energy that you burn up in the ejection of this electron. So we're just going to put in brackets here the energy used up in ejecting an electron. Now, you can see an equation that I have written down up with Einstein's explanation, E is equal to HF. We could also, by the way, let's rewrite it up here. E is equal to HF, HC over lambda. That equation is perfectly valid whenever you're doing a photoelectric effect problem. It's also valid whenever you're dealing with a photon, period. In the context of the photoelectric effect or anything else, that's a photon's energy. If that's the energy of a photon, then the work function, which is the minimum energy of a photon, would be what? If energy is HF, then minimum energy would be what? You've just got to draw a connection here with what we've just done. The equation's really, really easy to derive. If energy is HF, then minimum energy, or W, would be H what? Good. HFO. H times minimum frequency. Well, we could also say it's HC over lambda, but that lambda wouldn't be minimum wavelength. It would be Aaron? H times minimum frequency, HC over lambda maximum. We talk about the threshold frequency a lot more often than we talk about a threshold wavelength. The threshold frequency is the minimum frequency, but since wavelength and frequency are inversely related, if you have a minimum frequency below which no electrons are ejected, then you have a maximum wavelength above which no electrons are ejected. So our minimum frequency, our threshold frequency is our minimum frequency, our maximum wavelength, or our threshold wavelength is our maximum wavelength. There's a new equation. That's on our data sheet. That is on our data sheet. Now we've established this, right? Now that we've defined our terms, we'll reiterate it. If we're below the threshold frequency, nothing's going to happen. It doesn't matter whether you have one photon below the threshold frequency or 1,000 photons below the threshold frequency, nothing will happen. Photons above the threshold frequency will cause the electrons to be ejected. And it's a 1-to-1 ratio. So if you have a single photon above the threshold frequency, then you're going to have a single electron ejected. If you have 1,000 photons above, it's going to be 1,000 electrons that are ejected. You guys have seen in many different circumstances the photoelectric effect used before. Probably the most common one would be a solar cell of one type. Light strikes it. Electrons are ejected. It becomes an electric current. You're generating electricity. If you have the wrong kind of light, electrons won't be ejected. Okay, and as a kid, I remember in grade 6, I think it was, I had a solar-powered calculator. It was the coolest thing ever because solar-powered calculators were just coming in. They didn't work that well, but my solar-powered calculator when I was at school worked perfectly. When I took it home to do homework, didn't work. Didn't work very well at all. Occasionally, it would work a little bit. Okay. I thought, well, I'm smart. My calculator's not working. What do I need to do? I need to move it somewhere where I have more light. Increase the intensity of the light, right? It wasn't working at home because the light wasn't bright enough. It didn't work, though. Okay. I had the same idea that Hertz had in 1887. You don't get electrons ejected. You're not getting an electric current generated. You get more light. Okay, it made sense to me, right? But it didn't work. What I needed to do, and what I didn't understand that I needed to do, was not increase the amount of light. I needed to increase the frequency of the light. In other words, the light that we were using at school that was able to power my calculator, we were using a different kind of light in my house. It didn't have the higher band of frequency in that light in my house. So it wasn't going to work. Doesn't matter how much of it I had, it just wasn't going to work. The frequency was too low. We were below the threshold frequency. Now, if you are above the threshold frequency, then brighter light does matter. Okay. Above the threshold frequency, then again, it's a one-to-one ratio. So a single photon will cause a single electron. 1,000 photons will cause 1,000 electrons. But a photon that's way above the threshold frequency, way above the threshold frequency, is way above the minimum energy necessary. So the electron that's ejected is going to be more energetic in itself. Okay, back to the analogy, the demonstration that we did in class. Okay, if we struck our volunteer with a single photon that barely had enough energy, then we get an electron, an ouch, generated. But if we struck him with something that had way more than enough energy, then we'd still get a single ouch, but it would be a more energetic ouch. Okay? A single electron, a more energetic electron that's generated there. A couple more terms. The first one right now is going to seem a little bit like, really? What's the point? Okay, tomorrow I'm going to show you a picture of a little experiment that can be done in order to determine the threshold frequency of a metal. You might want to do that if you're designing a solar cell, determine the threshold frequency. Show you how to do it tomorrow. But for now, I'll just tell you what this term is. Tomorrow we'll use it a little bit more. Stopping potential. The symbol, by the way, is V stop. It's voltage, an electric potential. Once an electron has been ejected, it's moving, right? Certain kinetic energy. You can cause that electron to speed up or slow down. We did that back in Unit 2 with electricity. If you introduce a potential difference, you'll cause that electron to either speed up or slow down. We want it to slow down. In fact, we don't just want it to slow down, we want it to stop. So the stopping potential is the potential difference necessary to stop an already ejected electron. The photoelectric effect has already happened. The electron is gone. It's out of the atom now. But we want to stop it. We want to stop it dead in its tracks. We want the electron to be like a car going up the hill with a big enough hill to stop the electron, to stop the car. The potential difference necessary to stop an already ejected electron. Now, we can relate the stopping voltage to an equation that we've already seen before. The kinetic energy of the ejected electron is 1/2 mv squared. But that kinetic energy, as the electron slows down and stops, gets converted to what? As the car goes up a hill, the kinetic energy gets converted to potential. So we're going to say EK is 1/2 mv squared, but it also is equal to QV stop, the conversion of kinetic to potential as the electron stops. This equation is also on our data sheet, although it's not together on our data sheet. EK is equal to 1/2 mv squared is in one place, EK is equal to QV stop is in another place. We just put them together then. So what do we got so far? We got E is equal to HF equals HC over lambda. That's not a new equation. That's valid now, but it was also valid yesterday for other things as well. We've got W is equal to HF is equal to HC over lambda max. Okay, that's brand new, and that's valid just for the photoelectric effect. We also have EK is equal to 1/2 mv squared equals QV stop. That's valid for the photoelectric effect. Now the last one, before we do an example here. The law of conservation of energy says initial energy equals the final energy. When we're ejecting an electron here, the initial energy that we have, the energy that we start with, is the energy of the photon, right? What causes all this to take place? It's the light, the photon that has an energy equal to h times f. So this is my initial energy, what I start with. Tell me, please, what's the final energy? What is it that possesses the energy when the problem is done? The electron has been ejected. What has energy now? After the electron's been ejected, what is it that has the energy? The electron. What kind of energy does the electron have? Right. So we're going to say HF, the energy of the photon, is equal to the kinetic energy of the electron. But it's not true, because there's energy used up in the process. The initial energy ends up being equal to the final energy plus the energy used up in the process, the work function. It's kind of like this. Okay, you want to go to 7-Eleven and buy me a Slurpee. You have 10 joules of chemical potential energy stored in your body. You walk to 7-Eleven. You have 4 joules left in your body of chemical potential energy in your body. The initial energy wasn't equal to final. 10 doesn't equal 4. But the initial energy, 10 joules, equals what you end up with, the 4 joules, plus the 6 joules that you used up in the process. So 10 joules would be equal to the 4 joules that you end up with plus what you used up in the process. Or the initial energy, okay, the photon, would be equal to the final energy, the electron, plus whatever you used up in the process. Now, what we're going to have to do sometimes is replace terms in this equation with other equations that we've already seen. HF, for instance, could be replaced with HC over lambda, because they mean exactly the same thing. EK could be replaced with 1/2 mv squared or QV stop. W, the work function, could be replaced with HF0 or HC over lambda max. What you see up on the board there right now is mathematically everything you need to know about the photoelectric effect. There's the main equation, HF is equal to EK max plus W, which ironically does not appear on your data sheet. And then there's the ones that kind of go along with it, the ones in red, the easier ones that do appear on your data sheet. I've got 3 examples that I want to go through with you here today. Here's the first one, 14.4 on page 716. Blue light shines on the metal surface shown in figure 14.13. I don't care about the diagram, the surface, the picture of it all. It doesn't matter. Okay, we can do this without a picture. It causes the photoemission of electrons. In other words, electrons are ejected. The photoelectric effect has taken place. The photon had a frequency, don't know what it is, but we know it's bigger than the threshold frequency because the electrons were ejected. The stopping potential is 2.6 volts. Sometimes they call it the stopping voltage, 2.6 volts, required to completely prevent electrons from reaching the collector. In other words, if it's completely preventing electrons from reaching the collector, the electrons are being stopped dead in their tracks. We want to know what the maximum kinetic energy of the electrons are. Okay? We have a stopping potential of 2.6 volts. We want to find, it says the maximum kinetic energy there. Okay? We want to find the kinetic energy. Understand, when we find the kinetic energy of the ejected electron, it is the maximum value, because we don't really know exactly how much energy the electron will have. We just know that it can't have more than what we calculate. It could be less. If the energy conversion isn't as efficient as we think, the energy could be less, but it can't be more. So when we solve for this value, it will be the maximum value. All right, so what do you want to do? Well, let's real quickly paste the equations that we just identified as being valid equations for this concept. You want to find EK, the maximum kinetic energy of the electrons. We've got V stop. Which one do you think you're going to use? Got to be something up there, right? Yeah. Let's try EK is equal to QV stop. That's going to work for us. Okay. But even if Lucas had to give me a different one, a different equation, I would have went with it, because they're all valid. So even if he had to give me a different one, it's not wrong. This is just the one that's going to work for us right away. Okay. EK is equal to QV stop. So Q is 1.6 times 10 to the minus 19 coulombs. Because it's an electron, V stop is 2.6. Okay, let's get the value of EK there. 4.16 or 4.2, we'll say, times 10 to the minus 19 joules. Wait, I should have asked you that. How do you know it's joules? I should have asked you what unit it was. Joules or electron volts. How do we know it's joules there? Look, if you use standard units, coulombs and volts, you're going to get standard units out of it. You're going to get joules out of it. Okay, no trick there. Use this equation, you're never going to get the electron volts out of it. That seems easy enough, right? You're going to have 3 bits of homework tonight, just like you had last night. The first one is page 716, but I'm not going to give you a chance to work on that yet, okay? Because I want to make sure we can get all 3 of these examples done before the end of class here. 716, 1 to 3, that's your first bit of homework. Here's your second example. Experiments show that the work function for cesium is 2.1 electron volts. Determine the threshold frequency and wavelength for photons capable of producing photoemission. In other words, electrons are being ejected. Okay, what's the threshold frequency and the threshold wavelength? In other words, we're looking for F0, and we're looking for lambda, not minimum wavelength, but rather threshold frequency is minimum frequency, threshold wavelength is maximum. Yeah, maximum wavelength. Let's put in the equations again that we just identified a few minutes ago as being valid here. What do you want to try? What do you want to do here? The good news is, you put up your hand and you tell me something that's on the board right now, and I'm not going to make fun of you for saying something ridiculous, because they're all valid. I wouldn't make fun of you anyways, but. Okay, everybody else. Lucas, what do you want to do? What do you want to try there? Yeah. Good. That'll give me the threshold frequency, right? F0 is equal to W over H. W is 2.10 electron volts. What value of Planck's constant do you want to use there? We get 2 values. Which one do you want to use, Cassie? The 4.14 one, right? Don't need to know the exact number. Just look on your data sheet, right? 4.14 times 10 to the minus 15 electron volt seconds. What do we get for threshold frequency there? 5.07 times 10 to the 14 hertz. Good, thank you. Now, threshold wavelength, we're going to do almost the same thing, right? W is equal to H times C over lambda max. Lambda max is equal to HC over W. Same deal here, right? Same deal. Once again, 4.14 for Planck's constant and 2.10 for the work function. Now, if you don't like electron volts, what could you have done here? What can you always do? Always. Go to joules. Okay, convert the 2.1 to joules, and then use the 6.63 value for Planck's constant, right? So if that confuses you, when can I use electron volts? When can't I use electron volts? Just use joules, because it always works. In this case, the electron volts also works, but joules always does. Okay, we're going to do one more, and then we'll give you a chance to work on those 3 sets of homework that you have for tonight. This one says using table 14.1, which actually gives us work functions. We'll have to look that up. We want to determine the maximum speed of electrons emitted from aluminum if the surface is illuminated with this light. Okay, first of all, this is our wavelength. This is not our threshold wavelength. It's not saying this is the maximum wavelength. This is just the wavelength. It's lambda, not lambda max. We want to find the maximum speed. Okay, remember, when we're dealing with kinetic energy, it's always maximum kinetic energy. We just sometimes don't put the symbol max in for it. We also need the work function of aluminum. If somebody can look that up for me, please, on page 719 in chapter 14, that'd be great. We get 4.08 electron volts. Thanks, guys, for looking that up for me. We want to find the maximum speed. Let's paste those equations that we learned a few minutes ago, the ones that are valid for the photoelectric effect, and see which one or ones we want to try. Take a look. See if you can come up with it. Okay, too late. Time's up. Why did I say time's up? Why did I say it's too late? If you don't have an answer to that question for a photoelectric effect problem in 5 seconds, then I want you to use this one. I'm not trying to be sarcastic here. Okay? If it's this one that you're going to use, or this one, or this one, it's usually pretty obvious. You can come up with the equation you're going to try in probably about 5 seconds. If you can't come up with the equation that you want to try within 5 seconds, then automatically try this one, because it's probably the one you're going to use if you haven't identified it prior to that. Make sense? So by default, if you can't come up with an equation right away, use that one. Okay, let's try it. Let's try it here. We have HF is equal to EK max plus W. We don't have the frequency, but we've got the wavelength, so let's replace HF with HC over lambda. We want to find the maximum speed. Well, kinetic energy is 1/2 mv max squared. And we've got the work function, 4.08 electron volts. Okay, good. You want to find V. You want to find V here. Pay real close attention to what I'm about to say. This is the last big thing that I'm going to say today. 9 times out of 10, you can use joules or electron volts, whatever you want. But if you're using 1/2 mv squared or you're using QV stop, you must use joules. So if I left the equation like this, I could use electron volts or joules, whatever I want. But as soon as I introduce 1/2 mv squared into that, I got to use joules. Is that confusing? Is that at all confusing? I think it is. I think it is. What do you do if that doesn't really make sense to you? Just use joules always. Sometimes it's a little bit extra work, but it always works for you. Okay, let's solve for V here. Let's plug in our numbers, solve for V here. We got 6.63 times 10 to the minus 34 joule seconds for Planck's constant, 3 times 10 to the 8, divided by lambda, which was 125 times 10 to the minus 9. 1/2 of 9.11 times 10 to the minus 31 times V squared, plus the work function, which we said was 4.08 electron volts. Let's convert that to joules. We get 6.528 times 10 to the minus 19 joules. That's our new work function. Same work function, just expressed in different units here. Now let's solve it. Let's solve this. Let's get the left-hand side first. Let's say 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by, what is that, 125? Negative 9. Okay, there's a number on my left-hand side. Let's subtract from that 6.528 times 10 to the minus 19. Let's double that to get rid of the half. Let's divide by 9.11 to get rid of it. And then let's square root this to get V. And we end up getting 1.44 times 10 to the 6 meters per second. This is not the speed of the electron. This is the maximum possible speed that the electron could be traveling. Could be slower, but it can't be faster. That's the best we can do here, is calculate the maximum possible speed. Is that okay? If in doubt, go joules. If in doubt, go this equation, the one that doesn't appear on our data sheet. You've either got to remember that equation or you've got to figure it out the way that we just did. All right? So your homework tonight is the practice problems, obviously the ones that we just gave you here on page 716 and 718, but also on page 719. I think it's a total of 6 or 7 or 8 questions. Let's get those done for tomorrow. We'll take a peek at them, and we'll show you one more thing with the photoelectric effect with the graph. We'll be ready for our test on Monday.